the title of my talk, Logic Design Using Memristors. Now actually I have been working on various emerging technologies over the last 7-8 years, like reversible and quantum circuits and computing, then all optical circuits, designing circuits using all optical technologies, and very recently this memristors. But this does not mean that I work on the hardware, I actually design the circuits. No. I and my students, we design algorithms. I just take the problems from these domains. This memristor is a very new technology which has come up. Of course, the first products are yet to hit the market. It is expected that maybe in this year itself we will be seeing the first products based on memristors hitting the market. But what we have tried to do, we have tried to identify some of the important research challenges that exists in these new technologies. And you see, once the new technology comes, let's say once a quantum computer comes, you need software, you need a host of other set of tools so that a user can effectively use the system. So our research group mainly targets to solve some problems in those areas. So in this talk I shall not try to start with the algorithm challenges as such, because I thought it would be much better if I can at least apprise you very briefly about this new technology. What is this memristor all about? Okay? So with this background, let us try to first introduce to you what is memristor. Well, talking about the fundamental circuit elements, since your schools you have been studying on these. So how many fundamental passive circuit elements are there? 3. Resistance, capacitance, inductance. So resistance. So Ohm was the person who, you can say, I should not say invented, means identified the property of resistances. Then Henry, the inductance. George, the capacitance. Now, very recently in 1971, Leon Chua of MIT, he postulated the existence of a fourth fundamental circuit component, passive circuit component called the memristor. This is the symbolic representation of a memristor. So let us first try to understand what is this memristor. Now Chua's first paper was titled Memristor, the Missing Link. So what is this missing link? So we already had these 3 different circuit components, and now we have a fourth. So we shall see shortly that what is the missing link, that which was missing, and how memristor means aims to fill up that blank space. So a little bit of background. So as I said, so this was not discovered, it was theoretically postulated by Leon Chua. Leon Chua, through theoretical considerations, predicted the existence of a circuit element called memristor. Now the name memristor has come from the short form from memory and resistor. So I shall come to why this memory and resistor things are coming in here. You see, one basic property of a memristor, unlike the other circuit elements like inductor, capacitor and resistor, is, you can change the value of the resistance by applying some suitable voltage across it. And the most interesting thing is that once you have done that, and if you withdraw the voltage, the resistance value will remain. So the device can memorize the last resistance value. So this has opened up immense possibilities and applications, some of which we shall be talking about. Memristor essentially defines a relationship between magnetic flux and charge, which was so far missing. So the next slide will tell you about the missing link. You see, so we are all familiar with the four fundamental electrical parameters: current, voltage, charge and flux. And these are all well-known relationships which are already present in the textbooks you must have studied. Ohm's law, V equal to IR, Q equal to CV, phi equal to Li, and current equal to dq dt, rate of change of charge, voltage equal to rate of change of flux. Now you see, our nature is symmetrical, so one would expect that there should be a link here, which was so far missing. There was no property or device that could define a direct relationship between flux and charge. Now, according to Leon Chua's postulate, this memristor attempts to fill this void. Basically, memristor is related to flux and charge according to this kind of a relationship. Flux equal to some constant m multiplied by the charge. Now, this was postulated in 1971. So, it was about 37 years later, some of the researchers in HP labs in 2008, they accidentally came up with a device they fabricated which showed some peculiar characteristics. Then they dug into the previous literature, history, and then they could find Chua's paper. They found to their astonishment and surprise that this device very closely resembles the properties of a memristor which was predicted by Chua long back. Of course, later on it was found that, well, these group were not the first ones to fabricate a memristor device. It was even in the 1960s. Some of the devices with similar properties were fabricated and were studied, but no one knew about these interesting characteristics of those devices then. So they were learned much later. So essentially what this group of researchers at HP lab did, they fabricated a material using titanium dioxide. Just when we fabricate a diode in semiconductor, we take a silicon material, we put some impurities on the two sides. So in a similar way, you take a titanium dioxide material and on one side of it, you put some doping. These are called oxygen vacancies. Actually what it means, you dope with a material like Ti4O7, which has some oxygen deficiencies with respect to TiO2. In TiO2, the number of oxygen atoms will be double that of titanium, but here it will be a little less than that, Ti4O7. So there are other materials also. And this material were sandwiched between platinum electrodes on the two sides. So the characteristic of this material was that the original undoped region, titanium dioxide, was a highly resistive region. The resistance value was very high. But in comparison, the doped region showed or exhibited much lower resistance value. And in response to the applied voltage, the boundary between the two regions can be shifted. Yes, oxygen resistance. So, suppose this slab I was talking about. This was a silicon dioxide material. On one side, I have doped it with oxygen vacancies. So this part has lower resistance, this part has higher resistance. So suppose I put this, I am calling it a forward bias. I apply a positive voltage towards the doped side. then what will happen? These oxygen vacancies will tend to move towards the negative side because they are positively charged ions, and the overall resistivity of this slab will decrease. This is the low resistance state of the device. But in contrast, if we apply the reverse voltage, this is the reverse bias condition. Here the oxygen vacancies will be shifting towards one end, thereby increasing the resistance. Now the interesting point here is that these two states of the memristor, the corresponding resistance values are significantly different. Maybe in the on state, the resistance value can be of the order of hundreds of ohms, but in the off state it can be 10 kilo ohm, 20 kilo ohm, like that. So there is a very marked difference in the resistance value. So now you can think that, well, I have a device whose resistance I can change by applying a voltage. Now if I withdraw the voltage, my resistance value is remembered. The device remembers the resistance. So can I use this device as a memory? So in conventional MOS memories, we store the two states 0 and 1 typically, either in the form of a flip-flop or as charge stored in a capacitor, static RAM versus dynamic RAM, as you know. But here we have something called resistive RAM. We are using a resistance as a memory which has the capability of remembering its resistance value, and externally by applying a voltage I can change the value of the resistance. This is one application which is very promising. There are many others. Fine. So this is the overall picture I was talking about. This is the slab of the material, titanium dioxide. One side is undoped, other side is doped, and I can write down the overall resistance as this. W is the width of this doped region multiplied by this R low is the resistance per unit length of this region, and R high is the resistance per unit length of this region. R high is much larger. So as I said, by applying a suitable voltage, the value of W can be changed. This boundary will be moving right or left. Right? So this is what I said, resistive RAM. So you can use it to store digital information. Not only binary, you can also use it as a multi-valued memory. Not only two states, you can distinguish between 4 states. Let's say 100 ohm, 1 kilo ohm, 5 kilo ohm, 10 kilo ohm. Then you can store 2 bits in one device. Okay.
Does the resistance differ with the amount of voltage that you apply?
Yes, yes. I shall be showing you the characteristics.
And how long it will stay? How long?
Indefinite, you can memorize. So it is a property of the oxygen vacancies. They do not move if you withdraw the voltage. So not only titanium dioxide, subsequently many other oxide materials have been found to exhibit similar behavior. So there are many companies working worldwide. They are working on this design and fabrication of
And also
memristor.
reversible also. I think it's reversible process.
Yeah, you can again bring it back. Yes, you can again bring it back. Yes, reversible. Now, some of the interesting features of the memristor is that if I look at the cross-sectional area, it can be as small as 10 square nanometer. The smallest memristor that has been fabricated and reported has a cross-section area of 10 nanometer square. Now, you can compare it to the dynamic memory and the flash devices all of us are carrying, the pen drives. They have typically 40 nanometer or 20 nanometer features. So which tells you that memristor has the potential of providing you with much larger memory density, packing density in the memories. Now, I mean, it has been projected that with respect to the size of the pen drives that we are carrying, so how much is the maximum size of those pen drives? I have recently bought 256 GB. I think that is the maximum. You do not get more than that. But it is projected that these memristors, they are expected to come out very soon in the market. They will be carrying 1 terabyte of space in that same size. Not only that, they will be at least 100 times faster than the flash drives. Okay. So the first thing memristors will be replacing will be the flash memories. There are other applications also. So this 10 times is just a very conservative estimate. So it doesn't found that it can be 100 times fast. This of course is a DRAM. Sorry. This is not with respect to flash memories. With respect to the conventional dynamic RAMs, still memristors are slower. They are about 10 times slower. But you see, in the laptops that are coming in the market, the secondary disk memory is being replaced by flash memory, solid state drives. So once this technology comes, they will be replaced by memristor based drives. They will also be solid state, right? And their speed gap will be much less. Nowadays, how much is the speed of a secondary memory disk with respect to the main memory? So at least 1000 times, if not more. Now we are expecting to bring it down to 10. So you see, the entire gamut of computer architectures is bound to change once this technology comes. The concept of memory hierarchy will change altogether. The algorithms that you use for memory hierarchy, virtual memory, everything is bound to change. Okay. So these are some of the potential. Now this I am skipping. Now let us come to the most important and interesting part of memristors. Memristor can be used to design memory systems, fine. You need one single component to store, let's say, 1 bit of data, maybe multiple bit. So it means even in MOS technology you need several transistors to store 1 bit. But here in one memristor device you can store 1 bit. But you can also design some logic. Well, you can say that, well, in CMOS also we can design logic. So what is so great about memristors? So I shall come to this. Let's say when we design memory systems, how do we design? How are the memory cells organized? They are organized in a 2-dimensional array, very compact layout. So it is called a crossbar structure. There are rows, there are columns. So in memristor-based memory, there also we consider a crossbar-like structure, where the memristor devices will be sitting between every row and column, at the junctions of the rows and columns. Suppose I lay out the rows, then I fabricate the memristors. On the top, I lay out the columns, like that. Now, if we have a memory system like that in the form of a crossbar, lot of work has been done where it has been shown that memristors fabricated on a crossbar can be used to implement certain kinds of logic operations. There are many works. So we shall be briefly looking at 2 of them, imply and magic. Let's see how they work. Well, first let's look at imply. So what is the imply operation? So if you have studied switching theory or logic, you know, this P has gone here. This P implies Q means P bar or Q. So in terms of the gate representation, you can represent the imply operation like this. P bar or Q. And with respect to the truth table of the imply will be this. If P is 0, output will be 1. If P is 1 and Q is 1, then also it is 1. Only for one combination, P1, Q0, output is 0. This is imply. Now we shall see or show how we can implement this imply operation using memristors. But before that, let us look at the current voltage characteristics of a memristor, which again is very interesting. This is the real current voltage characteristics of a memristor, which exhibits hysteresis, some kind of a hysteresis loop. This is called a pinched hysteresis curve, and this point is at 0 voltage. And this you can simplify by using segments of straight lines like this. For our convenience, we show it like this. So, from the negative side, if you go on increasing the voltage, the current will go on changing like this. Beyond a point, it will abruptly switch to here. After that, if you decrease the voltage, the current will follow this path. Again, beyond a point, it will again switch here. So like this, it will continue. So what we see, that this curve has two distinct slopes. One, the less slanting one, corresponds to high resistance, and the other one corresponds to low resistance. So just by applying a suitable voltage, I can switch the device from low resistance to high resistance and vice versa. So let's say some voltage which is beyond this point, let's call it V clear. V clear can be used to switch it from on to off, and V set can be used to switch it from off to on, and let V con be some intermediate voltage which is not sufficient to switch. Okay, this is the characteristic curve of a memristor device. Now you can use just a couple of memristors and a resistance to build an imply gate. Let's see how it works. So the design is very simple. We simply use two memristors. There is a resistance to ground, and here we apply voltages V con and V set. So you recall, V set is this voltage while you are changing it from off to on, and V con is some intermediate. It may be here, it may be here. V con is some intermediate voltage. Now, you may ask that, well, I have designed a circuit all right, but where do I apply my inputs? And from where do I get my output? So PQ are the inputs, and I am expected to get the imply as the output. You see, here the basic philosophy of circuit operation is different. These are called stateful circuit operation. Here we are not applying the inputs as voltages like our conventional circuits that you know about, CMOS. Rather, the inputs are applied as resistive states of the memristor. Suppose I want to apply an input P0 and Q1. I make P off, I make Q on. Off means I used to denote 0, on I used to denote a 1. So I am adjusting the resistance state of the memristor to indicate whether I am applying a logic 0 or logic 1. And then I simply apply V con and V set. So what will happen? The output P implies Q, that will get stored in this memristor Q. The value of Q will be updated or overwritten. The new value will be the imply. Let us see how it works. And this Rg is a resistance which lies between R1 and Roff of the memristors. So this is the circuit that we showed. This is the truth table of the imply. Let us verify the first row. So I am applying 0, 0. 0, 0 means both are off. Let's take an example that off means 10 kilo ohm, on means 100 ohm. So by applying a suitable voltage across the memristor, suppose I have a mechanism to do that. So I am not showing it here. So I have made both of them as 10 kilo ohm and 10 kilo ohm. Then I apply Vcon and Vset. Vset is some high voltage which can switch it to the on state, and Vcon is some intermediate voltage, lower. Now, let's see what happens. So, since both the memristors are off, they are the high resistance state, I said they are off. So, there will be very little current flowing, okay, which means the voltage out here at this point will be close to ground because there is very little current flowing, very little voltage drop. So, if you look at the Q memristor, what will be the voltage across it? Vset on one side and 0 on the other side. So that Vset is the voltage which can switch the memristor to on. So this Q was 0, Q will switch to 1. But if you look at P, here you have much lower voltage, Vcon. This voltage is not sufficient to switch P. So P will remain what it was, but Q will switch to the on state. If you look at the other column, let's say the other three columns I am considering together, let's take this one, this 1 and 0. Suppose this is on 100, this is 0, 10 kilo ohm. So now this is conducting, so there will be a relatively higher current flowing through this. So the voltage here will be close to Vcon because there will be a relatively higher current flowing, and voltage drop across this low resistance will be much smaller. So here approximately Vcon minus something will be there. So the voltage across Q will be Vset minus Vcon. That will not be sufficient to switch. So it was 0, it will remain 0. So similarly for the other two cases you can verify, they will also be able to switch the states. So this is how a memristor imply gate works. Right? So I have showed you how a single imply gate works. Right? Fine. This is what I said. If this is 0.5, so it will be approximately 0.5. So they drop, if it is 1 volt, approximately 0.5 volt. This cannot switch, so it will remain at 0. Now, let us look at another way of designing circuits using memristor. This is called memristor aided logic, in short MAGIC, magic. Now in magic you do not need any resistances, only memristors. And just like your imply, logic states are all again represented as memristor resistances. And here, to evaluate a gate, there are two steps to be followed. First, the output memristor is initialized to some state. Second, we are applying a certain operating voltage in the input. I shall show. So regarding initialization, if we are using a positive gate like AND and OR, then we have to initialize the output memristor to 0. But if you are using a negative gate like NAND, NOR or NAND, then we would be initializing the output to 1. Let us see how the circuits look like. This is a schematic diagram of the 4 types of gates I am showing: AND, NAND, NOR and OR. Let's see this. These are 3 memristors. You see this memristor, one side is marked as solid, Solid means the site where the doping is there. This is the notation. So in AND, I connect the three memristors like this. All the solid ends on one side. Okay? These are the two inputs. So I initialize the inputs in a suitable way. And this is the output which is initialized to 0. I said for AND, initialized to 0. Then for gate evaluation, I apply some operating voltage V0 in the input. Now if both IN1 and IN2 are conducting, they are on, then only this voltage V0 will reach here, and the voltage across this output memristor will be sufficient to switch it to 1. But for the other combination 00, 01 or 10, at least one of these two memristors will be off. So the voltage will not reach here because very little current will be flowing, and this will remain at 0. NAND is very similar, but you see the only difference in NAND is that the last memristor, the polarity is reversed. That is the only difference, nothing else. And I had said that for a negative gate, the output is initialized to 1. So let's say if I apply 1, 1, now in this case V0 will be a negative voltage. So apply a voltage, this voltage will come here, and this is a negative voltage. The voltage across this will be sufficient to switch it. So it will become 0. 1, 1, 0. For the other cases, there will be no switch, it will remain 1. Okay? So using magic, we can implement all 4 kinds of gates. But we shall see, I shall show it a little later, that with respect to the crossbar, you can only implement NOR because of the polarity. I shall come to it. So I am skipping a few slides because I have already explained. Yeah. Crossbar, as I said, it looks like this: rows, columns with memristors fabricated in between. Memristor crossbar, as I said, is a very compact way of laying out the memristors. So you can imagine I have a matrix kind of a structure, rows and columns, memristors are sitting at every junction. I am treating the whole thing as a memory. Some of the memristors is in state 0, some of them are in state 1. So the whole crossbar matrix I can represent it as by a binary matrix with elements 0 and 1. 0 indicates off and 1 indicates on. Okay. Yeah, at least one of the projectors have come out. Fine. So this state can be represented by a binary matrix. Now, there is a problem in crossbar. Let me just mention that problem and possibly one solution. Suppose I have stored some data in my crossbar memory and I want to read the value of one of the memristors. There is a problem called sneak path. It says that, well, you are trying to read the value of a particular memristor, but because of some phenomenon, the value you are reading out may be wrong. Okay, how does it happen? Let's take an example to illustrate. This is called the sneak path problem. Suppose I have a crossbar like this. Okay, rows, column, these circles denote the memristors. Suppose I want to read the state of this memristor. So how can I read the state of this memristor? So a very simple way is that I apply a voltage on the row and I measure the current that is flowing in the column. So if this memristor was conducting on, then a relatively high current will be flowing. But if this memristor was off, very low current will be flowing. So I apply a voltage on the row and I measure the current flowing in the, there will be some current sensors here. This is one way in which I can measure or sense whether the memristor is in 0 or 1 state. This will be the current flowing path. Okay. Let's call this cell as Cij. So as I said, if Cij is in the 0 state, it will be high resistance, so very low current will be flowing. But if Cij is in the 1 state, then there will be a high current flowing. Now what this snake path problem tells that, well, if you forget the environment, if you can forget the other memristors, then it seems to be quite fine. But suppose the memristor was in the 0 state, means you are expecting very low current to be flowing. But because some of the other memristors are in the on state, so there may be a bypass path through which the current might be flowing. So you are sensing a high current, you are incorrectly deducing that your memristor was in the 1 state, but actually it was in the 0 state. So 1 means high current. Yeah. Now what I am saying is that suppose there is a scenario like this. These 4 memristors were also in the 1 state, on state. Then what might happen? You just see. Suppose this was in the 0 state, so you are expecting very low current to be flowing. But because these green cells are 1, these are 1, so there will be a current, there is parallel current flowing path through this pathway. So you will be sensing a high current. There will be a parallel path through which the current is flowing. This is called the snake path problem. So whenever you are using memristor in memory or any other means application where you want to read the value of the memristors, you should be aware of the snake path problem. Now I am not going into theory of it. There are very nice papers where very nice graph theoretic algorithms have been proposed to detect and mitigate this snake path problem. Okay? There are very interesting algorithmic applications here. So I am just giving the result, what has been found out. Okay, this already I mentioned. There is a concept of an isolated zero rectangle. It says that, well, in this crossbar, you can define imaginary rectangles. Consider this is an imaginary rectangle, and you consider the corner memristors. Here there is a 0, there are 3 ones. So this rectangle is said to be an isolated zero rectangle if there is a single 0 in the corner and 1s in the other 3 corners. So what this formulation says is that if you can detect that there is a rectangle like this, then there is a possibility of snake path problem to happen. So you see there is another example. This is also an isolated zero rectangle. This is 0, 1, 1. So this is exactly what was happening. You are trying to read this, but there was a parallel path through which the current was flowing. This is because of the isolated zero rectangles. So I am just mentioning this, I am not going into the solutions. So if you can design the crossbar, store the values in such a way that such isolated zero rectangles will never occur, then it is guaranteed that the snake path problem will not affect your readout operations. Right? Okay. Now let us come to the crossbar. See, imply can be implemented in crossbar array like this. You consider this 1 row, 1 column. These are 2 memristor connected to the junctions. Just to connect the resistance in the row, you have an imply gate. Similarly, you think of magic. This is a magic NOR gate. NOR gate, you recall, this is on the other side, doping. You see, this gate can be directly mapped like this. You check. This input is on the solid side. So the inputs are coming from here. You see, these are the solid directions, solid. So the outputs are here, they are connected together. These two are connected together. And this connected point goes to the thin side of the output memristor. Goes to the thin side of the output memristor. The thick side is connected to ground. The thick side is connected to ground. So you see, when you fabricate memristor in the crossbar, there can be millions of such memristors. So you will be fabricating them in the same way. So the solid or the doping part will be all on the same sides. So you see, for a NOR gate you can map it directly like this. But if you want to map an OR gate, one of the memristor would have to be reversed in the direction. But that normally will not be in the crossbar, right? We will fabricate all of them in the same way. That is why we say that only NOR gates can be mapped efficiently on the crossbar or can be mapped on the crossbar. Now you think of a scenario. I am not going into the detail because in this short time it is very difficult to talk about everything. Now let us say you are wanting to map some algorithm or some function into circuit. You start with your original function or original means algorithmic specification, whatever. You map it to a circuit consisting of only NOR gates. Then there are many ways. This is again an algorithmic challenge in which you can map the NOR gates into the crossbar and evaluate. The crossbar allows you to have very high level of parallelism. You can map, let's say there are 3 NOR gates, so you can map them like this or you can map them like this. There are many ways you can map. Depending on the way you are mapping, you can evaluate the gates one by one sequentially or you can evaluate them in parallel also. There are several papers which have been published in the recent years which actually does this. So now you have, let me move away from the slides. Now you have a technology where you create a crossbar memory where you can store data by applying voltages to the rows and columns. You can also carry out some computations there. Like there are papers which show how you can design adders, multipliers and other functionalities on the crossbar. So you can implement virtually anything. Crossbar will be bigger, size will be bigger, but you can implement anything. So here you have, you can say the promise of a non-von Neumann kind of an architecture that is emerging. So what was von Neumann architecture? You had the processor, you had the memory, there was a pipe connecting the processor and the memory. You fetch instruction through the pipe, fetch data through the pipe, write back the data through the pipe back into memory. So this pipe was a very busy part of the system which is called the von Neumann bottleneck. So in order to improve performance, you have to make your memory bandwidth much higher. But that itself is a challenge because memory speed is much slower than CPU processor. So now we have a technology where you can say CPU is coming inside the memory. You can do computation in the same fabric where you are storing. So there is no need for sending data in and out, in and out. And so recently there have been 3 or 4 papers which have been published on something called in-memory computing or computation, where some large functions have been mapped into this crossbar memory, assuming that data is already there, data are already there, and by applying voltages you are also carrying out computation on the same data. So this is just the beginning. There is a lot to do. So there is a perspective of a number of interesting non-von Neumann architectures to come up. Okay, now coming to your query.
I got it.
No, but
Yeah.
still,
Yes.
let me share a few things with you.
Yeah.
This memory and computing is of course one application. There are several other applications where researchers are actively just working on. One is neuromorphic computing. Memristors can very efficiently implement the neural networks because you can, just by adjusting the value of the memristor resistance, you see, by applying a suitable voltage you can change the resistance.
Which can be changed.
So you can say that for a neural network, for a threshold gate you can change the weights. So there is a lot of work which are going on where people are seriously trying to build models of the brain using memristor networks. So this is one area where people are actively working on neuromorphic computing.
One problematic there, because one neuron is connected to 10 to the power 4 neurons and one dendrite is there. This 10 to the power 4 connectivity will be different.
That is different, but at least
Yeah.
the conventional neural network people are talking about,
Sure.
they implement it using that. Yeah, you're right.
Yeah.
That scale is much
Yeah.
beyond. And there is, okay, this is what else. And of course, the second one, as I said, that it will be very quickly replacing the flash memory drives. So all SD and other cards are available, they will possibly get replaced by memristor based memory devices. And okay, von Neumann, non-von already talked about. And what else?
Data flow, it can be data flow basically.
Data flow basically, yeah, data flow.
flow.
And I'm missing out what else I thought just now, one more thing.
Dynamic mapping can be done.
Dynamic mapping, non-von Neumann architecture, this already I've talked about. Okay, yeah. And means I just mentioned before that that memory hierarchy. Now you think of a computer system where you do not have any secondary memory. So your entire memory is like your primary memory. So your entire computer architecture design is bound to change. You don't need any memory management unit, no virtual memory mapping. So once the speed of the DRAM and the memristors can be bridged, so a single memory, a single level memory hierarchy can be possible. So there are a lot of opportunities, but there are challenges also. As I said, this sneak path is one of the major issues. But the big advantage is that this is a non-volatile technology. You do not need a power supply to retain the contents, and it also dissipates very low energy. Static energy dissipation is nil.
This sneak path can be handled, can be crossbar, can be 3-dimensional, then it can be neural like.
Yeah, we are working on that.
Yeah.
Building crossbar like this, row column. Yeah. There are a lot of things, but there are fabrication challenges, people are working on it. So as I said, so exactly our students, our research group, what we are doing, we have identified these problems. We have identified the in-memory computing architectures. But now the bigger problem comes. Starting from a high-level algorithm, how can we map that algorithm into that hardware? So we are working on that. Those are purely software algorithms, graph algorithms, different kind of heuristics, optimization. So we are basically working on those things.
Or finding algorithms from data, that is the A&M problem.
So what actually Professor Colin Paul also talked about, so I am also talking in similar terms. So we have an architecture which can be customized, which can be reconfigured. See here memristor has another advantage of reconfiguration. The same memristor which just now you use to compute an addition, maybe a little later the same circuit you will use for multiplication. Just the control circuit will be changing the voltages to be applied, just that. So for those of you who are familiar, it is somewhat similar to that microfluidic biochips, digital microfluidic biochips. So the area is the same. By changing the voltages, you can do different computations in the same area. So your entire challenge of developing the design tools will be different. So there are a lot of challenges. So that ends my talk.
Thank you very much.
Now, I would like to call upon Professor Dr. Shubham Mukherjee, felicitate Professor Indranil Sengupta